So today we're starting with logistic regression. And note that logistic regression is not a regression algorithm to start with, right? The name is a misnomer. So actually it's a classification algorithm. But you'll find out why it was named logistic regression very soon, right? So like I've said before, logistic regression is used to classify stuff like email, for example. A logistic regression algorithm was used to classify whether an email is spam or not spam. That's an example. And that example is like an online transaction. So online fraud detection companies use classification algorithms to determine whether a transaction is fraudulent or not. Or in the hospital, we can use the classification algorithm to determine whether a tumor is malignant or benign. So classification algorithms are as important as regression algorithms. They are very important in machine learning and in the real world, right? So in this case now, our output variable, which is y, is a real number, which is either 0 or 1. So that means it's either yes or no. So either it's spam or not spam, or it's fraudulent or not fraudulent, or it's malignant or it's benign. So 0 here is the negative value, while 1 here is the positive value. Just to note as well, we can have multi-class classification where we could have something like 0, 1, 2, 3, or even 4, right? So it's not every time that it's binary. It's not every time that it's just one. It's just 2 options. We could have as much as 5, 6 options, right? Where the data set is classified into 3, 4 groups, right? So this is multi-class. It's called multi-class classification problem. So let's see how a logistic regression problem looks like on the graph. So we'll have something like this, right? And then we have x-axis like this. So we have here, we have 2 more sides here. For example, so we are using the 2 more sides to determine whether a tumor is malignant or not. So here we have here. So here we have yes. And on this plane, we have no. So we have the middle of the hyperplane here. And then we have let's say there's an imaginary line here. Right? So on this plane we have something like this. Right? Or no, let me not let me do like this without the line. So we have this here, and then on the no part we have this. I mean, this is just to show you how logistic regression output variable looks like on the graph. I'll show you why we cannot use a linear regression model to fit a logistic regression problem because it just doesn't work, right? So a linear model doesn't work because if I was going to apply this linear model, I would say this is the middle of my hyperplane, right? So everything here, everything in this place means no, and everything in this place means yes. But look at this. It means that I'm going to classify all this here, right, and then I'm going to put this in another class. So however way you decide that you want to fit your logistic regression problem, it won't go. Like it just won't go. Right. So let's see. So here's an example of a training set for classification tasks, like I've said. And if we use our linear regression, which is, if you remember, h of theta x would give us, let's just use the normal equation, right? So it's a transpose of our theta and our feature variable on our input variable, right? But if you want to make a prediction with logistic regression, what we need to do is to put a threshold classifier output, right? A threshold classifier output. This is what I mean by a threshold classifier output. Okay, let me use this as well. Let me use this as well. So without something like this. Something like this. Right? Where this is 0.5. So any prediction that falls between this plane, right, gives us a yes output or a malignant output. And any decision that falls within this plane, right, gives us a benign output. So if we make a prediction, so we are saying if h of x is greater than or equal to 0.5, then predict y equals to 1, or if h of x is less than 0.5, then predict y equals to 0. So in essence, we are saying that unlike linear regression, where our y was greater than 1, right? Unlike linear regression, and I'm sure this is very obvious to you, unlike linear regression, where our output could be greater than 1 or greater than 10 or greater than 100. In logistic regression, we have something like this. It can't give an output greater than 1 or less than 0. So we have something like this. We have 0, right? H of x, 1, right? So this is the output that we can have in logistic regression. We can have either and in a binary logistic regression. Anyways, so you could either have 0, right? Our output spans from 0 to 1. So let's look at a representation, hypothesis representation, right? So our logistic regression model, our logistic regression hypothesis. How do they spell hypothesis again? Hypothesis representation, right? So we'll have something like this. Excuse me. So our logistic regression model now give us this is h of x right? And usually, if we were going to use linear regression hypothesis, if you remember, our linear regression hypothesis, if you scroll back to your normal equation class, our linear regression hypothesis was this, was h of x this x is in the bracket, right, equal to theta transpose x, right? But for logistic regression, we'll modify it a little. So, but for logistic regression, our hypothesis representation will take a little form. So what we'll do is that instead of this, we're going to have h of x. We're going to have h of x equals to, so we'll put this inside the g. So we'll have g into theta transpose x, right? And then we'll define the function g. Then we'll define the function g as g into z equal to 1 over 1 plus e raised to power minus z. So this is what we call this logistic function or the sigmoid function. It's called the sigmoid function or the logistic function. So this is where this got its name from, its logistic regression name. So it's not a regression algorithm. The regression here is what we would like to call a misnomer, right? It's a classification algorithm, but it got its name from this function that's called the logistic function, right? So if we take the two functions and put it together, here's what we'll get. If we take this function and this function and put it together, we're going to get h of x equals to 1, that's this g, right? 1 over 1 plus e raised to power z. This z is going to be what? Obviously, it's going to be theta transpose x, right? So equals to 1 over 1 plus, this is 1, plus e raised to power minus theta transpose z. Sorry, transpose x, right? So obviously, what we just did is that to say that our z equals to theta transpose x, right? So we can draw this again to show you what the sigmoid function looks like on a 2D graph. So it flattens out here, then meets this at -5 at 0.5, and then flattens out again. Right, so this is g of z. This is z, which is equals to theta transpose x, just to remind you. Right, it meets here at 0.5. So everything in this plane meets at 0, and from here meets at 1. So I mean, this just fits the hypothesis representation very much. It doesn't get simpler than this. So we are saying that if we carry out a probability or a logistic regression project, and we find out that let's say the percentage or the probability of malignancy is, let's say, 70%. Obviously, anything between 51% to 99% will be classified as 1, right? And anything between 0.1 to 4.9, right? Or sorry, between 10% or between 1% rather to 49% will be classified as 0. That's just what this hypothesis representation is telling us. So after that, now let's move into decision boundary to better understand what or how logistic or classification algorithms work. So once again, let's remind ourselves that our h of x equal to g, which is a function of theta transpose x, and now our g into z equals to 1 over 1 plus e raised to the power minus z, right? So we want to understand how or when this hypothesis makes prediction and understand how what the hypothesis function looks like. So suppose in number 1 now, right, in the first instance, suppose we predict y equals to 1. So we predict our prediction gives us y equals to 1 if h of x is greater than 0.5. Remember I said that in our hypothesis representation. So if h of x is greater than 0.5 here, of course our y will be equals to 1, right? But this will happen when g of z, this g of z, it happens when g of z is greater than or equals to 0.5. Right, so let's see how that looks like. So let's see how that looks like. So we have this, and we have hypothesis representation looking like this, right? So we are saying that this, I mean, this is just straightforward, is in this bucket, right? So if we have our g of z, this is our g of z in this bucket, then our z, which again, once again, equals to theta transpose x, is going to be in this bucket, right? So we are saying that since the hypothesis equals to g of theta transpose x, right? And we are saying that this g of z, right, needs to be greater than or equal to 0.5. Then theta transpose x, which is our z, right, needs to be greater than or equal to 0. So this is what we are trying to get to, right? Because at the end of the day, don't forget that we are trying to solve for theta, right? To be sure of our accuracy. So at the end of the day, theta transpose x, right, needs to be greater than or equal to 0, right? And approach, obviously, this is from 0 to positive is here, then from 0 to negative is there, right? So it's going to be obviously greater than or equal to 0. On the second plane, here was number 1. On the second plane, if we predict that y equals to 0, I mean, this is just as easy as it can get, and that's why it was chosen as the excuse me, the algorithms of choice for beginners, because it's just very simple. If I teach you k-means or SVM, then you get very confused. But now on your own, you can be able to pick up other algorithms and check out their mathematics. So if we predict that y equals to 0 this time around, if h of x is less than 0.5, right? So let's draw g of z, and then we have z on this plane. So we are saying this is 0.5. Okay? So we are saying we have g of z in this plane, and then we have our hypothesis in this plane, right? So in this half, g of z is less than 0.5, right? This just so that you don't think all this g of z is just bullshit. So I need to show you on the graph. So g of z, if g of z is less than 0.5, then our z, right, is going to be also less than 0. This is 0. Here our z was greater than 0, right? So our z here will be less than 0. So just to put it in proper lingua, g of z was less than 0.5, going to be less than 0.5 when z, which is equals to theta transpose x, right, is less than 0. So let's use this to understand how logistic regression makes its prediction, right, by using of the decision boundary. By using of a decision boundary. So let's say we have h of x is equals to g into theta transpose x, but theta transpose x will be something like this: theta 0 plus theta 1 x1 plus theta 2 x2. Don't forget, this is not a direct multiplication. Like, this is basically what we know as theta transpose x. So it's a transpose, it's not a direct multiplication. I think I've shown you that. So let's say our theta 1 now, our theta 0 is equals to -3. Our theta 1 equals to 1, and then our theta 2 equals to 1. Let's just give it an arbitrary value. So our theta will be equals to, in a vector form, 3, 1, 1. right? So we are predicting. So we are predicting y equals to 1 if what? If theta transpose x is greater than or equal to 0. So if theta transpose x is greater than or equals to 0, right? So we are predicting y equals to 1 if minus 3 plus 1x, that's plus x1 plus x2 greater than or equals to 0. Of course, once again, this is your theta transpose x, right? So what we can do is that we can take minus 3 to the other side. So what we would have is x1 plus x2 greater than or equal to 3, such that x1, right, is greater than or equals to 3. So we can say that x1 is greater than or equals to 3, and then x2 as well is greater than or equal to 3. So this will help us draw a decision boundary. So this will help us draw a decision boundary. We would have 1, 2, and 3. We would have 1, 2, and 3. So our decision boundary looks like this. So any data set that falls between here, that falls at the bottom of the decision boundary or at the top of the decision boundary, right? So this is our hyperplane. If you remember in linear regression, we had an hyperplane, a decision boundary that gave us our predictions. This is the decision boundary in logistic regression that gives us our decision. So anything that falls within here, for example, is y equals to 1, so it's malignant. Anything that falls here is y equals to 0, so is what? Is benign. I cannot use 4, 5, 10 variables to show you how this works. I could just use something that is very simple, right, to show you how logistic regression works. So this is just like a simple intuition. After today on Monday morning, we'll be looking at Python. Right, so I'm going to be coding everything that we've learned so far. So if you have any questions, please ask me. Thank you very much.